Hello, Dan here from howtomechatronics.com. In this tutorial, we will learn how to make an Arduino-based RC receiver. Since building my DIY Arduino RC transmitter in one of my previous videos, I got a lot of requests from you guys to make a dedicated receiver for it. So here it is. Now these two devices can easily communicate and we can use them for controlling many things wirelessly. I will explain how everything works through few examples. In the first example, we will use this Arduino RC receiver to control a simple car consisting of two DC motors. In the second example, I will show you how to control brushless motors and servos, which are common components found in many commercial RC planes, boats, cars and so on. If we know how to control them, we can easily modify and control many RC models with our own custom-built Arduino transmitter. Therefore, as a third example, I will show you how I modified and used this Arduino-based RC system to control this commercial RC car. I must say that driving this thing with your own controller is so fun. Nevertheless, to begin with, let's take a look at the circuit diagram of this system. The radio communication is based on the nRF24L01 transceiver modules. The transmitter constantly sends data from its controllers, the joysticks, the buttons, the potentiometers and the toggle switches, and we receive this data with the receiver. For more details how the transmitter works, you can check my other detailed tutorial for it. There is a link to it in the description of the video. We can also note here that this RC receiver doesn't necessarily work with only this particular transmitter that I built. It can work with any other similar setup consisting of an Arduino board and an nRF24L01 module. Nevertheless, the brain of this RC receiver is an Arduino Pro Mini board. For powering, we can use either the VCC pin to which we can connect 5 volts or the raw pin to which we can connect from 6 to 12 volts. Note that there are two versions of the Arduino Pro Mini, like the one I use here that operates at 5 volts and the other that operates at 3.3 volts. On the other hand, the nRF24L01 module operates at 3.3 volts, so therefore we need a voltage regulator. This time I am using the AMS1117 voltage regulator, which outputs 3.3 volts from inputs which can range from 5 to 12 volts. For communication with the Arduino, the nRF24L01 module uses the SPI protocol, plus 2 additional digital pins. That means we are left with 9 digital pins which can be used as output channels, 2 of which are the RX and the TX pins. It's worth noting that these pins must be disconnected from anything while we are uploading a sketch to the Arduino board. So therefore I made it possible to be connected or disconnected through separate pin headers. Actually, we can also use the analog inputs as digital outputs, so although this Arduino board is quite small, we got plenty of output or channels available. Nevertheless, in order to keep the circuit compact, I made a custom PCB design using the EasyEDA free online circuit design software. Here I arranged the 8 channels right next to a 5 volts and a ground rail, and so we can directly connect servos and ESCs to them. The channel number 9 is located at a separate position, near the VCC pin of the Arduino, so we can use, for example, an ESC for powering the Arduino with its battery eliminator circuit feature, which provides 5 volts. Of course, we could use any other channel for that purpose, as the VCC pin is connected to the 5 volt rail as well. As for the channels 7 and 8, we can see here how they are interrupted with these pin headers. If we want to use them, we just have to connect the two pins together. The programming header is located at the top right corner, and the 100 microfarads capacitor serves for both the voltage regulator and the nRF24L01 module. On the bottom left corner of the PCB, I place the analog input pins. Here we can note one more thing, and that's that some Arduino Pro Mini boards might have different pins arrangements. So therefore I included one more version of the PCB, so you can choose the one that matches with your Arduino Pro Mini board. Once I finished the design, I generated the Gerber file needed for manufacturing the PCB. Then I ordered the PCB from JLC PCB, which are also the sponsor of this video. Here we can simply drag and drop the Gerber file, and once uploaded, we can review our PCB in the Gerber viewer. If everything is alright, then we can go on and select the properties that we want for our PCB. And that's it. Now we can simply order our PCB at a reasonable price. Note that if it's your first order from JLC PCB, you can get up to 5 PCBs for only $2. After several days, the PCBs have arrived. The quality of the PCB is great and everything is exactly the same as in the design. Now we can move on and assemble the PCB. First, we need to solder the pin headers of the Arduino board. A convenient way to do that is to use the breadboard to stick the pin headers in it, and so the board will stay firmly in place while soldering. As I said earlier, depending on your board, the pins might vary a bit, so keep that in mind when soldering them. Also, there are some ground pins that we need to leave free, as there are some traces running on the PCB under them. Once I soldered the Arduino board, I cut the excess length of the pins. Next, I placed all other pin headers in place. We need both male and female pin headers, or actually it's up to you what pin headers you will choose to use. However, it is a good idea to use male pin headers for the digital channels, as the servo motors and the ESC's connections are female, so in that way we can easily connect them. The voltage regulator is a surface mount component, so I used some blue tack adhesive to hold it in place while soldering. Lastly, once we solder the two capacitors in place, we can attach the nRF24L01 module to the appropriate pin headers. Depending on the application or the range that we need, we can either use the normal module with the onboard antenna or the one to which we can attach a bigger antenna, and so achieve wireless communication of up to 700 meters in open space. So that's it, our Arduino RC receiver is now ready and we can use it for anything we want. For programming the receiver or connecting the Arduino Pro Mini to the computer, we can use an USB to serial UART interface, which can be connected to the programming header. In the Arduino IDE Tools menu, we need to select the Arduino Pro or Pro Mini board, select the proper version of the processor, select the port, and select the programming method to USB ASP. And with that, now we are able to upload codes to the Arduino. Okay, now we can move on and take a look at the first example. It's a simple car consisting of two 12V DC motors, and in some of my previous videos I already showed you how it works and how to build it. This time we will use our new Arduino RC receiver for controlling it. So the connections are really simple. The 12V coming from the batteries go to the 12V pin of our receiver, and the 6 control pins of the driver go to the 6 channels. We need to note here that in order to be able to control the speed of the motors, we need to provide PWM signals to the enable A and enable B pins of the driver. In our receiver, the channels number 2, 3, 6 and 9 can output PWM signals, so therefore I connected the enable pins of the driver to the channels number 2 and 6 in this case. Let's take a look at the Arduino code now. So first we need to include the SPI and the RF24 library, define some pins, the radio object and the data structure where we will store the incoming data from the transmitter. In the setup section we need to define the pin outputs and begin the radio communication. For more details how this works and what each of these lines do, you can check my detailed nRF24L01 tutorial. In the loop section we constantly check whether we are receiving data, and if we do, we read that incoming data. If we take a quick look at the transmitter code, we can see what kind of data it sends to the receiver. It reads the data from all its controllers, the joysticks, the potentiometers and the buttons, and it sends that data as a single package to the receiver. So once we read that data, we can do whatever we want with it. In this case, we will use the joystick 1 y-axis value for controlling the throttle and the x-axis value for controlling the steering. I put this data into separate throttle and steering variables. The values we are getting from the joysticks are from 0 to 255. So if we move the joystick down, we will set the driver control pins appropriately so the car moves backward, and use the throttle value for controlling the speed of movement. The same principle applies for driving forward, left and right. Again, I already have detailed tutorial on how this car works, so you can check that out for better understanding. At the bottom of the code we can note the reset data custom function, which resets all values to their initial default values, so in case the radio communication is lost, the car will stop moving. Okay, now we can move on with the second example, controlling servos and brushless motors using this Arduino RC receiver. For controlling brushless motors, we need an ESC, or electronic speed controller. The Arduino communicates to the ESC with just a single pin. For controlling the ESC, the Arduino sends a specific PWM signal to the ESC, and with it, the ESC controls the motor speed. I must say again that I already have detailed tutorial for this topic as well, so for more info you can check that out. I will put links to all related tutorials in the description of the video. The ESC with that same connection provides 5 volts through its battery eliminator circuit feature, so we can power our receiver with it as well. As for the servo motors, they have the same type of connections as the ESC, and we can simply attach them to any of the channels that are available. The input signals for controlling both servos and brushless motors using ESCs are almost the same. They use specific 50 Hz PWM signal, which can be easily generated using the Arduino servo library. So after receiving the data from the transmitter, we convert the values from 0 to 255 to values from 0 to 180 for controlling the servos using the bright function. In similar way, we convert the data for controlling the ESC to values from 1000 to 2000. Using the servo library write microseconds function, we send the PWM signal to the ESC, and so we can control the speed of the brushless motor from minimum to maximum. So this is how we can control most RC planes, cars, boats and so on, as they are usually using this type of motors, servos and brushless motors. In my next video I will show you how I use this Arduino RC receiver to control my DIY Arduino RC airplane. Yep, you heard it right, I made a fully functional Arduino based RC airplane, which I can control it with my DIY Arduino RC transmitter. So buckle up for the next video, but until then let's finish this tutorial with the third example, modifying and controlling this RC car that I bought from Banggood for 15 bucks. The RC car came with its own controller which can control the front wheels to move left and right, as well as move the car forward and backward. However, as it's a cheap RC car, the controls are digital, or either on or off, to maximum position left and right and maximum speed. Regardless of that, I disassembled the car to see what's inside and how I can implement the Arduino RC receiver for controlling it. Once I uncovered the electronics components, I noticed that the two motors are actually simple DC motors that operate at 5 volts. Even the front motor, which controls the limited movements for the steering, is a simple continuous rotation DC motor. So apparently we already know how to control DC motors, so replacing this circuit board with our DIY Arduino RC receiver will be quite easy. In addition to our receiver, we just need a motor driver capable of driving two motors at the same time. There are plenty of options for that purpose, even the one we used in the first example, the L298N driver. However, that one is too big for this application, so I chose the MX1508 motor driver. This is a simple dual DC motor driver which features H-bridge and PWM control. It has 4 control input pins, 4 pins for the motors and 2 pins for powering. I desoldered the motors connections from the RC car circuit board and soldered them to the driver. On the back side I soldered the power pins, and what's left now is to connect the driver with the receiver. The power for this RC car comes from 4.8 volts nickel cadmium battery located at the bottom of the car. So using jump wires I connected these pins to the VCC pin of the Arduino and also connected the 4 control input pins of the driver to 4 digital channels. As I said earlier, this driver supports PWM control. So for the motor B or the rear motor, I use the PWM channels number 2 and 3. The code for this RC car is very similar to the first example. We use the data coming from the joysticks to control the throttle and the steering of the RC car. For moving backward, we use the analog write function to send PWM signal to the driver at the input 3 pin, while we hold the input 4 pin low. For moving forward, we do that the opposite way. If the joystick stays in the middle, we give command to the driver to brake or stop the motor. The same principle is used for the steering motor, although here we don't have to use the analog write function as we don't need to control the speed of the motor. After uploading this sketch to the Arduino, I just had to reassemble the RC car. I placed the small driver in the inside housing and secured the rest of the parts with the screws. I reconnected the receiver with the driver and placed it under the outer housing of the car, which had enough place to fit in the receiver. So not only we modified this car to be controlled with our own DIY RC transmitter, but also improved it by adding PWM control so we can also control the speed of the car. So that's pretty much everything for this tutorial. I hope you enjoyed this video and learned something new. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.